Question number 51. A certain gas takes 4 times as long as to effuse out as helium. Its molecular mass will be. This is a process of effusion. Gas is effusing from a hole, and one thing is given that gas takes 4 times as longer as helium gas. If I talk about rate of effusion or rate of diffusion, it depends on two things. One is the time taken by it, number one. Number two, its molar mass also. To understand the relation between the rate of effusion and the molar mass is the law that's given by Graham. That's called Graham's law of diffusion. That we'll use here. And similarly, if I talk about the time utilized during the process of effusion, that also decides the rate. So this rate of effusion of that unknown gas, suppose that is Rg, that is equal to certain mass divided by the time taken by it. So we can say this Rg is inversely proportional to Tg for that particular gas. This Tg is the time taken by that gas. Rg is the rate of effusion of that particular unknown gas. Further, similarly, if I talk about helium, this rate is again inversely proportional to time taken by helium to effuse. These two relations we have. Further, if I talk about Graham's law, that Rg is inversely proportional to the root of molar mass of that gas. Similarly, if I talk about helium, this Rhe is inversely proportional to 1 by root Mhe, that is the molar mass of helium. On the basis of these two rules, we will find out the actual molar mass of that unknown gas, because we know that the molar mass of helium is 16 gram per mole, and on that basis what would be the molecular mass? That is definitely 16U. So in this case, if I talk about the relation between these two, so we can represent this relation if I divide this Rg by Rhe. So the relation would becomes Rg by Rhe is equal to The by Tg, the simple relation. Similarly, if I relate the molar masses, then it would be equal to root of molar mass of helium would be here, and root of molar mass of that gas would be here. We have this relation. Now let's compare the time and the molar masses here. Time taken by helium is suppose x, then definitely that gas will take time, that is 4 times of x. So instead of writing The, I'm just writing here x, that is considered as the time taken by helium to effuse. Further, time taken by gas to effuse is the 4 times of this x, and that is equal to root of molar mass of helium, that is 4 divided by mg. We don't know this. That's why I'm just using this mg here instead of that. So in this case, it would becomes 1 by 4. So squaring both sides, you will obtain 1 by 16 is equal to 4 by molar mass of that gas. So this mg would becomes equal to 16 into 4, that is 64 gram per mole. This is molar mass. And what would be the molecular mass in this case? Definitely the molar mass becomes 64U. So just choose option 4 as the correct option, because the molar mass of that unknown gas is 64U. After that, question number 52 is here. 4 mole of an ideal gas expanded spontaneously in vacuum. The work done will be. In this case, we have the 4 moles of the ideal gas. It is expanded spontaneously in vacuum. If I talk about vacuum, in that case, this P external would be 0. There is no external pressure in vacuum. And we know that work done is equals to negative P external delta V, the simple case, and P external, this whole value is 0. So definitely this work done would becomes 0. So which answer should be correct? Definitely option 2 you can choose as the correct option, because work done would be 0 in this particular case. After that, question number 53. If at 77 degrees Celsius the temperature is given, enthalpy of fusion of a compound is 140 kilojoule per mole. It means for 1 mole of the substance, the amount of heat absorbed for the process of fusion is 140 kilojoule. Then the entropy change in joule per Kelvin mole during the fusion will be. In this case, we have enthalpy of fusion. That's given. What's that? That is 140 kilojoule per mole. Or it can also be written as 140 into 10 raised to the power 3 joule per mole. This is given in the question. Temperature is also given, that is 77 degrees Celsius, or it can be represented as is equal to 350 Kelvin. This would be the temperature. Now, entropy change for this process. It means entropy for fusion you need to just identify. What's the relation? The relation is N delta H for fusion divided by temperature of the process of fusion. Very simple question. And in this case, the total amount of energy for the 1 mole of the process, it means enthalpy of the fusion is given, that is 140 kilojoule. So just place the values here to find out the correct answer. We are considering 1 mole here. Delta H for the fusion is 140 into 10 raised to the power 3, because answer we need to just find out in joule per Kelvin per mole. That's why I have changed this 140 kilojoule in joule. Now divided by 350. Now if you solve this, you will find out that this answer is 400 joule per Kelvin mole. Where this is given? This is given here in option 2. So just option 2 would become the correct option for this particular question. Question number 54. Kp by Kc for the given equilibrium is, if we consider this reaction PCl5, it's getting changed into PCl3 and Cl2, equilibrium is established, and you need to just find out the ratio of Kp and Kc. What's the relation between these two? We know that Kp is equals to Kc RT raised to the power delta N, you know. And in this case, this Kp upon Kc would becomes RT raised to the power delta N. Delta N is the change in the number of moles while reactant is getting changed into product. So this delta N would becomes, delta N is N2 minus N1. What is N2? The moles of the product. N1 is moles of the reactant. So for the product there are 2 moles PCl3 and Cl2, and for the reactant there is 1 mole only. So that's why this N2 minus N1 becomes 2 minus 1. That's why it is 1. So this value we have, this is 1, and on the basis of this we'll place here RT raised to the power 1. It means we have the correct relation between Kc and Kp, that is equal to RT. The ratio of Kp to Kc is RT, and this is correctly given here in option 4. After that, question number 55. Which of the following equimolar aqueous solutions of hydroxide will have the highest pH? Highest pH means which has the maximum basic character. If you look at the given options, we'll identify that these all are the hydroxides of alkaline earth metals. If we talk about alkaline earth metals, the order is first beryllium, then magnesium, after that calcium, and then barium. And we know that if you move down the group, if we talk about beryllium, magnesium, calcium, and barium, and if we consider the hydroxides of all of these, hydroxides of beryllium, magnesium, calcium, and barium, if I consider, then definitely as you move down the group, the basic nature increases. And on this basis, this option 4 becomes the correct option for this particular question, because barium hydroxide would be most basic and that would have maximum pH, highest pH.